Welcome back, dear students. This is Ramana Sir Physics. We are discussing most important IPE LAQs we are discussing. So in that last two classes we finished oscillation LAQs and work energy power LAQs also we finished. And the last chapter in the IPE first year, intermediate first year AP and TS. Okay, last lesson, that is thermodynamics. Thermodynamics. Okay, from thermodynamics, one LAQ compulsory they can ask. There are two LAQs are there. So one is the Carnot engine, second one is second law of thermodynamics, working of heat engine and refrigerator. So these two long answers are there. Any one compulsory in both the states. Okay, so today we'll discuss about the Carnot engine. How they'll ask question. In Carnot engine, first they'll ask the definitions of reversible, irreversible process. Afterwards, they'll ask the working of Carnot engine and efficiency, the derivation they'll ask. So in this, okay, first we'll discuss the definition of reversible and irreversible process. Here, reversible process means what? In Carnot engine, reversible process means the process in which we can retrace back the previous stages. So in such a way, the system passes to the same as that of original states, and finally the system and surroundings return back to the same states, that meaning original states, called reversible process. Example, we can take fusion of ice and vaporization of water. We can take example. So these stages we can bring back to the previous stages, that meaning here for example the water, okay, freeze to ice. What happened? So then the ice we can bring to the form of water. So like that only vaporization of water. So the water we can evaporate. Okay. So again if we condense, what happened? It return back to the water state. So one form to another form. So that form to again previous original form we can bring back. So that process is called reversible process. We can bring back. So we can reverse that process to original process. That process is a reversible process. Irreversible process means we cannot retrace back original state. So that process is called irreversible process. For example, diffusion of gases and the burden against friction. This process we can take for irreversible process. We cannot bring back the previous states, that meaning original states we cannot bring back in this. So that process is called what? Reversible process. Now Carnot engine. Our topic is what? Carnot engine. Here Carnot engine. So in this, the working substance maintained between two temperatures. So that are T1 and T2 temperature. Okay, it operates between the two temperatures T1 and T2, between T1 and T2. So this Carnot engine operates. Here Carnot engine mainly consists four parts, four components it consists. The first one is cylinder. It consists working substance. In this, the walls of the cylinder so made up by non-conducting materials. So base part of the cylinder is mainly purely conducting, and these walls are non-conducting, and this is fitted with a non-conducting frictionless, okay, movable piston. Frictionless movable piston it consists. Okay, it consists the fitted with the non-conducting frictionless movable piston, so we can move, okay, so freely. It consists, the cylinder consists what? Working substance. As a ideal gas we can take as a working substance. Okay, the second component is source. The source maintain high temperature, the T1 Kelvin, just infinite thermal capacity. And another component, third component is sink. Sink maintains lower temperature at T2 Kelvin. It maintains, it is also infinite thermal capacity. And the last part, fourth part, this part is called insulating stand. Insulating stand purely made up by non-conducting material. Non-conducting material. So on this non-conducting material insulating stand, we can put cylinder, so which consists the working substance. So these are the four components a Carnot engine. The Carnot engine, so mainly four operation takes place. Okay, so in this working substance, the four operations we can observe with the help of the graph also. So you can observe here. So first of all, the working substance, whatever ideal gas or another any gas. Here, the first initial pressure P1, volume V1, temperature T1. So first we are allowed to expand. So what happened at constant temperature? So that time what happened that time? So T1 only at constant temperature we are maintaining, and pressure is changes. Pressure is changing from P1 to P2 and V1 to V2. The first A to B, this is isothermal expansion. Now afterwards what to do? So B to C, so we are allowed to expand adiabatically. So that time the components physical variables all changes, pressure, volume, temperature. The pressure changes to P2 to P3 and V2 to V3 and T1 to T2. So then like that only, next C point to D point. The B point to C point is called adiabatic expansion. C point to D point is isothermal compression. Like that only D point to A point, adiabatic compression. These four operations now we have to discuss with the help of the equations. The first one, operation 1, the isothermal expansion from A to B. So here we can observe here from A point to B point. So the cylinder is okay. So allowed to the cylinder which consists the working substance allowed to expand isothermally, means at constant temperature we have to allow. Here pressure is changing from P1 to P2 and volume is changing from V1 to V2, and but temperature T1 is T1 only, so is constant. So this is first one is called what? Isothermal expansion. So we can write also here isothermal expansion. Isothermal Worden formula, we know that W1 is equal to isothermal Worden formula, we know that what is the formula? W1 is equal to W1, so that is equal to heat we supplied. So the Q1 is equal to what is the isothermal Worden formula? RT1 log the final volume by initial volume. Their final volume is V2, initial volume is what? V1. V2 by V1 to the base A. So this is the first operation, that is isothermal expansion. The second operation we'll discuss, the operation 2, adiabatic expansion. So that is from B to C. Here the cylinder containing working substance is placed on insulating stand. So that time what happened that time? The gas, the temperature of the gas so falls from T1 to T2. Falls from T1 to T2. Adiabatically expansion takes place here. So the temperature falls from T1 to T2. The second process is called what? B to C. This is called what? Adiabatic expansion. Here the Worden on the system, say W2. W2 equal to what we can take? W2 equal to R by gamma minus 1 into the temperature T1. So falling from T1 to T2. So that is T1 minus T2. T1 minus T2. So this is the adiabatic expansion from B point to C point. So next operation 3, isothermal compression. Here from C to D. So the cylinder consists working substance placed on sink. So at constant temperature, what happened that time? Isothermal compression takes place. The C to D is what? Isothermal compression. Temperature is constant, but here the gas is compressing. So that is why the Worden W3 equal to, that is minus Q2. That is equal to R. Okay, what is the formula? R T2 log the final volume to initial volume from C to D. The final volume is what? V4 by initial is what in this case? V3. V4 by V3 to the base A. Here what I'll do? The negative sign I'll take here. The V3 by V4 I want to take. That is why before I am writing negative W3 is equal to minus RT2 log V4 by V3 becomes V3 by V4. Why? Because we taken here minus we taken to the base A. Operation for adiabatic compression, that is from D point to A point. So here again we have to keep the cylinder on non-conducting substance. So what happened that time? The non-conducting substance whenever placing time. So what happened that time? So the adiabatic compression takes place again from D point to A point. Again it comes to the original state, it will come. So that is why the D point to A point. So this is called what? Adiabatic compression. Here D to A, adiabatic compression. The Worden formula. So W4 is equal to, what is the formula? R by gamma minus 1. R by gamma minus 1 into the temperature differences. Here T2 minus T1. T2 minus T1. Here also negative sign I'll take common. So what happened that time? Minus into R by gamma minus 1 into T1 minus T2. T1 minus T2. So this is the fourth operation in Carnot cycle. Total net Worden is how much? W equal to, so we can write W1 plus W2 plus W3 plus W4. Here add these all four Wordens. What happened that time? W is equal to W1 is what? RT1 log V2 by V1 to the base A plus second one is what? R by gamma minus 1 into T1 minus T2, and third one is what? Minus RT2 log V3 by V4 to the base A, and final one R by gamma minus 1 into T1 minus T2. So it is very clear, R by gamma minus 1 into T1 minus T2 minus R by gamma minus 1 into T1 minus T2 gets cancelled. The remaining is what? Done. W is equal to, how much we got? RT1 log V2 by V1 to the base E minus RT2 log V3 by V4 to the base E. Here the final Worden we got. Now we have to calculate the efficiency of Carnot engine. Next, efficiency of Carnot cycle. The definition of efficiency of Carnot cycle is the Worden to heat supplied to the system. The efficiency of Carnot engine is what? The Worden to heat input. That is, according to the definition, Worden efficiency formula is what? Worden by heat supplied, heat input also you can take. Substitute the values. The efficiency eta equal to the Worden, the net Worden just now we got, how much we got? RT1 log V2 by V1 to the base E minus RT2 log V3 by V4 to the base E divided by heat supplied Q1. Q1 is how much? RT1 log V2 by V1 to the base E. V2 by V1 to the base E we got. So we can write eta equal to, here what? Q1 minus Q2 by Q1. That equal to, we can write, therefore that equal to eta equal to 1 minus Q2 by Q1. This is efficiency in terms of heats. Like that only in terms of temperature also. So we have to derive. Here we know that adiabatic relation. So what is the formula? TV gamma minus 1 is equal to constant. TV gamma minus 1 is equal to what? Constant. We know that formula. So that meaning is what? T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1. So we'll apply in adiabatic cases. In diagram we observed just now. So from B to C and D to A both are adiabatic. In that B to C I am applying. So I am applying to, so for B to C, okay, what are the points? B to C. B points are what? Here we know that P2 V2 T1. Here C point is what? P3 V3 and T2. Apply this formula for B to C. What is the formula here? TV gamma minus 1. Here T is how much? T1 and V is what? V2 power gamma minus 1 is equal to, at C point apply here, T is what? T2 and V3 power gamma minus 1. Like that only apply to D to A point also. D to A. So apply. So this is for adiabatic compression. Adiabatic compression. What are the coordinates here? D point. What are the P4, V4, T2, and here coordinates are what? P1, V1 and T1. P1, V1, T1. Substitute here. Here first I am writing this one. T1 V1 power gamma minus 1 is equal to, applying here, T2 V4 power gamma minus 1. Here equations I am keeping, this one I am taking equation 1. So here equation 2 and here equation 3 I am taking. Here equation 2 divided by 3. Left hand side by left hand side and right hand side by right hand side. Equation 2 divided by 3 I am doing. Equation 2 divided by equation 3. What happens? Equation 2 left hand side is what? T1 V2 power gamma minus 1 divided by equation 3 left hand side is what? T1 V1 power gamma minus 1 is equal to equation 2 right hand side T2 V3 power gamma minus 1 divided by T2 V4 power gamma minus 1. Here T1 gets cancelled, T2 gets cancelled. Here V2 by V1 is what? V2 by V1 power gamma minus 1 is equal to, here V3 by V4 power gamma minus 1. V2 by V4 power gamma minus 1 equal to V3 by V4 power gamma minus 1. Both the sides, what I am doing, the powers I am cancelling both the sides. Therefore, what we can take, V2 by V1 is equal to V3 by V4. So this V2 by V1 is equal to V3 by V4. I am substituting in equation 1. Equation 1 implies efficiency formula is what? RT1 log V2 by V1 to the base A minus RT2 log, instead of V3 by V4 I am writing V2 by V1. V2 by V1 writing to the base E divided by RT1 log V2 by V1 to the base E. Here numerator you can observe log V2 by V1 to the base E. Here also log V1 to the V2 by V1 to the base E same only. And R also there, we can take common. R eta, the efficiency eta equal to, I am taking common R into log V2 by V1 to the base E, I am taking common. The remaining is what here? T1, here remaining minus T2 divided by RT1 log V2 by V1 to the base E. Here RR gets cancelled and log V2 by V1 to the base E, log V2 by V1 to the base E cancel. The eta equal to what? Remaining T1 minus T2 by T1. Therefore, efficiency, finally, therefore, efficiency of Carnot engine eta equal to, we can write T1 by T1, that is 1, you can write minus T2 by T1, T2 by T1. So this is the final efficiency formula for Carnot engine. Efficiency eta equal to 1 minus T2 by T1. So if you write these all steps, you'll get 8 by 8 marks. So maybe attachment problems, very rare cases they'll ask for this question. So why? Because already this is lengthy and more equations are there. So that is why the complete answer, if you write, you'll get 8 by 8 marks. I hope all are understood. The next topic is the second law of thermodynamics. So that is completely theory part. So now I'll discuss that. The next one, second law of thermodynamics. The last question, state and explain second law of thermodynamics. Working of heat engine and working of refrigerator, the laws. Here the second law of thermodynamics states that, so it is, the heat always flows from higher body temperature to lower body temperature, and it states that any heat engine cannot perform 100% efficiency. So this is called second law of thermodynamics. So the two scientists, one is Clausius, another one is Kelvin. So the both the scientists gave explanations, statements given. Okay, the same, this one only, second law of thermodynamics. We will see the statements. The first statement you can observe, Clausius statement: it is impossible for a self-acting machine unaided by an external agency to transfer heat from a body at lower temperature to another at a high temperature. The second one, Kelvin statement: it is impossible to construct a heat engine operating in a cycle to convert the heat energy completely into work without any change of working system. Now we can observe the heat engine, working of heat engine we can observe. So you can check the diagram on the screen. So the mainly the heat engine consists of three components. One is hot reservoir, that is nothing but source. Second one, cold reservoir, that is nothing but sink, and working substance. Here three components it consists: the hot reservoir, that is nothing but source, okay, cold reservoir, that is sink, working substance. In heat engine, the working substance absorbs heat energy Q1 from the source present at high temperature T1. After doing some work W, it rejects heat energy Q2 to the sink present at cool temperature T2. Now overall, a complete cycle, the work done W equal to how much? Q1 minus Q2. We know that efficiency of heat engine is how much? Eta equal to W by Q1. So that is, W is what? Q1 minus Q2 divided by Q1. So that is 1 minus Q2 by Q1, that is equal to 1 minus T2 by T1. So this is the heat engine, the efficiency case. Next we will see the refrigerator. A refrigerator is a heat pump which is at the reserve of heat engine. The working substance extract heat Q2 from the sink at temperature T2. Some external work W is done on it and heat Q1 is released to the source at temperature T1. You can observe on the diagram also, this one. Okay, you can observe on the diagram. Next, the coefficient of performance of refrigerator is given by alpha equal to what? Q2 by W. So Q2 by W is what? Q1 minus Q2. Here what is the difference? Heat engine and here refrigerator. In a heat engine, heat cannot be fully converted into work. Likewise, a refrigerator cannot work without some external work done on the system. So that is, alpha cannot be infinite, meaning W can never be 0. On this both the cases, thermodynamic cases, so one numerical question also there, so they can ask the numerical question. So now let's see on screen the question. A refrigerator is to maintain eatable kept inside at 9 degrees centigrade. If room temperature is 36 degrees centigrade, calculate the coefficient of performance is. Here given T1 is given 36 degrees centigrade, but we have to convert into Kelvin. So that capital T1 equal to what? T1 degrees centigrade plus 273. To convert Kelvin purpose, we have to add plus 273. 36 plus 273, that is 309 Kelvin. And T2 is given 9 degrees centigrade. So that is, in converting to Kelvin, T2 equal to 9 plus 273, that is 282 Kelvin. We know that the coefficient of performance alpha equal to, what is the formula? T2 by T1 minus T2. T2 by T1 minus T2. So that is alpha equal to, T2 is how much? 282 divided by T1 minus T2, 309 minus 282, that is 282 divided by 9 minus 2, 7. Here 10 minus 8 is 2. Okay, so here what happened? So here 27. 282 by 27. Solve this one approximately. Okay, you'll get alpha equal to, after cancelling, 10.4 you'll get. Here no units. Why? Because this is purely constant. 10.4. This is 10.4. Okay, so I hope all are understood. So these are the LAQs. Another LAQs for oscillation and work energy power LAQs I given in description. So go through that. I hope all are understood. So here, along with numericals, we discussed all the LAQs. Okay, so please like, share. This is Ramana Sir Physics. Please subscribe this channel. Thank you.